In the previous lectures, we were able to understand how the nuclear spins for spin half system alpha and beta tend to align with the magnetic field B naught, results in a bulk magnetization M naught, which when applied a pulse along the transverse plane, in this example given as B1 along the y-axis, results in precession of this magnetization along the xz plane, and if you properly time your pulse, then you would effectively achieve the magnetization along the x-axis, which when kept a coil here will be picked up as a free induction decay. We also saw that the signal m plus of t would be given by m plus of 0 times exp I omega t times exp minus r2t. This signal is what we call as the free induction decay, and the m plus of 0 is the signal at 0 time when you start acquisition. This oscillation part, when Fourier transformed, gives a resonance at plus capital omega, where the capital omega is offset from the carrier frequency where you apply the pulse, and this is the relaxation part which comes up as line width for the resonance that we tend to observe. When this signal is Fourier transformed, we end up getting the frequency domain spectrum, as we call it, at plus omega, given by the specific relaxation rate. We have also extended this topic to understand how scalar coupling comes up for AX, AX2 and AMX type systems, such that we understand we get a doublet for each of the case here, and in this case you end up getting a triplet with a certain intensity ratio for A, while you get a doublet for X. And this case would have been solved by you to understand, depending upon the magnitude of coupling between A and M, M and X and A, you would be getting doublets of doublets, or just a triplet when the magnitudes are equal. Having understood this, we should also summarize a few limitations of the Bloch equations. Although even coupling doesn't exactly be explained by Bloch equations, we were able to understand that for the four given states that are present, we can imagine an M naught that is present for each case. For instance, you're talking about the V coupling case, where the chemical shift difference between the A and the X spin is much greater than that of their scalar coupling. In this case, we said the A dot X term gets approximated to only the AZ XZ term without the AX SX and without the AX XX and the AY XY terms. For the sake of simplicity, even the weak coupling limit can be imagined where you have an M naught for each one of this, which results in resonances at these positions. However, when you try to extend it to the strong coupling case, where in the strong coupling case, the magnitude of chemical shifts or precession frequency difference is in the order of the J coupling between the spins, in which case the terms AX XX plus AY XY cannot be set to 0 anymore. Then you have to see what ends up happening. The Bloch equations end up failing in such a case. Bloch equations cannot also explain what would be the result following application of pulses to transverse magnetization in a homonuclear coupled case without any ad hoc assumptions. Additionally, magnetization transfers for forbidden transitions, for instance, transitions that go double quantum and zero quantum, cannot be explained when the spin system is not in equilibrium. So therefore, Bloch equations have its own set of limitations. However, to first order, you are able to understand how the manipulation of the magnetization can be obtained with the help of pulses. In order to develop a thorough understanding, instead of looking at the bulk magnetization, we have to be looking closely into the spins that contribute towards this phenomenon. So in this lecture, we will be continuing to look at the same phenomenon, but instead of looking at the bulk magnetization, we'll be spending more time looking at the wave function. You will soon understand that drawbacks of Bloch equations can nicely be overcome by looking at the quantum aspect of these spins. So let us start with a basic expansion of this wave function. I hope you remember some of the basics from quantum chemistry where the wave function helps you get all information about the system. And this wave function can be expanded in terms of a superposition of states where the states here are a complete set of orthonormal bases that we expand the wave function in. This wave function that we talk about here has its time dependence, which is why I'm writing it as capital psi, can have the time dependence either on the coefficient or on the states. Since the states that we are looking at are stationary states, the time dependence comes into these coefficients. So therefore, let's take a little moment to understand how to get these coefficients. You take any state m and try to take the integral with respect to psi, then you are going to end up getting an integral such as this, where the summation is over n. In such a case, you are able to understand that you started with an orthonormal basis set. So only when n equal to m, you are going to have a non-zero integral on the right hand side. So m equal to n, you are going to get integral of the state n with respect to capital psi will give you Cn. So therefore, the psi that you had written up, which is a summation of Cn over the states n, can now be rewritten as summation over n, and just moving whatever we found to here, which will be integral of n to psi with respect to n. Since this is a number, you can always move to the other side. So therefore, capital psi will be given as integral over n ket n bra n times psi. If you pay close attention, on both the sides you have the ket of psi. So all that indicates that this has to be equal to 1. So this immediately implies that summation over n over the states where you have ket n to that of bra n will be given as identity. Identity, of course, in the dimension n by n based on what is the level of dimensionality that you have here. So this is an important identity that we will keep using as we go forward. So let's take a simple example of a spin half system. So in that case, we can write capital psi as C alpha times alpha plus C beta times beta. Here I am representing the wave function such that only the nuclear spin exists. Other degrees of freedom also exist, but let's not get into those right now. We will be able to incorporate them as we go forward. This is a simplistic discussion that we will have to start with, and we can always add things as we go forward. And here, what you are able to see is that you have to ensure that this wave function is normalized, in which case you are going to end up getting things of this sort. So when you have a psi star, you got to take a star of this, so you're going to end up getting alpha C alpha star. You're going to get 4 terms, which will also have alpha C alpha. Since these are just numbers, you can take them outside, and since we started with an orthonormal basis set, the integral of alpha to beta or beta to alpha will be 0, so therefore these two terms go to 0, and of course these two terms will also end up getting you 1 since it's an orthonormal basis set. So you end up getting something like C alpha star C alpha plus C beta star C beta, which is nothing but mod of C alpha square plus mod of C beta square. If you want to normalize them, so you're going to end up having, it's going to be equal to 1. What is the meaning of this C alpha is that the mod of C alpha square gives you the probability of finding the spin in the alpha state, while mod beta square gives you the probability of finding the spin in the beta state. How is the way we measure things in quantum mechanics is that you try to get the expectation value. This expectation value is defined by this equation, which you will be remembering from your quantum chemistry course, where the denominator just ensures that you have a normalized wave function to begin with. And if we satisfy this condition, the denominator goes to 1. So I'm just going to be writing the numerator. In order to make sure we are expanding properly, we'll be expanding the ket psi with respect to n and the bra psi with respect to m. Remember, when you take a complex conjugate, you're going to get the coefficients having a star on top of them. So the ket is going to be summation Cn. The ket is going to be summation Cnn with A being the operator, and the bra part is going to be summation Cm star, summation over m, and the summation over n, bra m. So therefore, this can be now rewritten as double summation Mn Cm star Cn bra m A ket n. The time dependence of the wave function exists here, while these are the stationary states of the system, and therefore this part of this equation just implies it's the matrix element of the matrix A with respect to m and n, while the time part exists here. So therefore, if you are able to extract this, most of your work is done. Before we get here, we will take a look at how a matrix representation of an operator looks, in particular in NMR. Let's take for a spin half system, you have two states alpha and beta, and these can be represented as shown here as matrices. So these two will be column matrices given by 1 0 and 0 1. If you recollect what you would have learnt about the angular momentum operators, Iz and I comma mi gives you h cross mi times I comma mi. So we can think about the operator A as the Iz operator. In which case, if you want to write the matrix form of the Iz operator, you would end up creating a matrix of this sort. Where the first element will be alpha Iz alpha. Immediately you understand, since the functions are eigenfunctions of the Iz operator, you understand these two terms would immediately go to 0. On the other hand, all this would end up doing is to pull the quantum number out of each one of them. So therefore, you're going to end up getting h cross by 2, 1, 0, 0, minus 1. And an important thing to note here, if you remember, we had written MAN, where A is the operator, M and N are the states that are present, where this is the Iz alpha alpha, and this is the Iz of alpha beta, Iz of beta alpha, and then Iz of beta beta. Therefore, the M can be alpha beta or N can be alpha beta, with the A operator being the Z operator. So therefore, you have a matrix representation for the Iz operator here. So similarly, we can also get the Ix operator, but unfortunately you do not have the functions which are eigenfunctions of the Ix operator when we have made it as an eigenfunction of the Iz operator. So in order to get Ix, you have to get the I plus and I minus. Similarly would be the case for Iy, where you have to get it plus I plus minus I minus by 2i. Okay, so now let us write what will I plus and I comma mi give you. This is going to give you h cross times square root of I minus m times I plus m plus 1 times I comma mi plus 1. So what the ladder up operator does is to leave the I quantum number unchanged, and by incrementing the mi quantum number by 1 unit with this given constant up front. Remember that the ladder up operator cannot ladder up beyond the highest state. So similar would be the case with the ladder down operator, where the only changes would be in these places, where ladder down operator will result in reduction of the mi quantum number by -1, and the coefficients end up changing this way. So let us try to operate I plus on the alpha state, which is half comma half. This will be equal to h cross square root of. Remember, for a spin half state, the spin 3 by 2 state does not exist, so therefore this will result in 0. Even if you forget that aspect, you are able to see here that this already goes to 0, so therefore the entire answer you get is here is 0, which makes sense. On the other hand, I plus on beta will be equal to. This makes sense because minus half plus 1 takes you to plus half, which will be the alpha state, and you are able to understand the entire coefficient goes to 1, so you are going to get something like h cross on alpha. So similarly, let's also repeat I minus on alpha. This will be given by So I minus will therefore demote alpha state to the beta state with a coefficient that will be equal to 1. So you're going to get H cross on beta. Similarly to the fact I plus on alpha is 0, I minus on beta would be 0 because you cannot demote any less than the beta state. So therefore, let's quickly write the I plus operator. I plus operator will be given by alpha I plus on alpha and we just saw the fact that you cannot promote alpha to any bigger state, so therefore these go to 0, and when you promote I plus on beta you go to alpha, so this will also go to 0 since alpha and beta are orthogonal. The only element that will exist will be that one, which is the 2 1 element, which will be 0 1 0 0 for I plus. Similarly for I minus, you are able to understand that I minus on beta state will be 0, so you can write 0 right away. On the other hand, if you promote the I minus on alpha here, that will go to beta state, but alpha beta will be 0, so this will go to 0. You'll understand that you'll get H cross right there. With these two written up, we should be able to get what is Ix because we have the I plus and the I minus operators written out here. Therefore, the Ix operator is going to be H cross 0 1 0 0. I'm going to put the H cross by 2 because there is a 2 right here, plus 0 0 1 0. So you get the Pauli's matrices for spin half system, which will be 0 1 1 0 for Ix. If you patiently repeat the same process for Iy, you will end up getting something like IH cross by 2 0 minus 1 1 0. So far what we have done is to write the operators for the Iz matrix and the Ix and the Iy matrices. There are some important aspects for you guys to observe here is that when you take Iz times Iz, which will be, the way you have to do this is that you need to take the transpose of 1 and then do it. So you're going to get H cross by 2, since it's a diagonal matrix, you're going to have same even when you take the transpose. So this will be equal to H cross by 4, you have to take square, so therefore this will be 1, 0, 0, 1. This is the identity matrix for 2 by 2. So therefore mod Iz square is given by 1 by 4 E 2 by 2. Similarly, let's try to do Ix transpose times Ix. This will be equal to H cross by 2 times H cross by 2. Since you are squaring it, the elements would remain where they are because there is no distinction that ends up coming. So this will be H cross square by 4. So taking the product, you're going to end up getting 1. And taking a product here will be 0, 0, 1. So this is also H cross square by 4 times E times 2 by 2. You got to be careful when you take Iy transpose times Iy here because you got to take a complex conjugate as well. So therefore you're going to get minus I square H cross square by 4 times 1, 0, 0, 1, which will once again be H cross square by 4. So let's see whether whatever we built up is correct. Because if you do a summation of Ix square plus Iy square plus Iz square, you're going to get 3 times 1 by 4, that's going to be 3 by 4. This is not surprising because this will be equal to I square, and I square on I is given by H cross square times I into I plus 1. With I being half, you're able to understand it comes up as 3 by 4. So here what we have seen so far is that operators can be represented as matrices, and we have just represented the spin half matrices, the Pauli matrices for spin half systems, which we'll be looking into detail. So going back to whatever we had earlier, we are able to appreciate the fact these elements are known to us provided we know the nuclear spin state that we are talking about. The moment we are able to determine what are these coefficients, your game will be done. So let us start from there. So the expectation value would be given by a double summation over m and n, Cm star Cn, m times a times n. Since this has the time dependence, this can also be written as another operator called the projection operator, which is given by ket psi times bra psi, where when you apply this on a state n, p, m, let us see what we get. this is going to be expanded as CNN, and this is going to be expanded as Cm star bra m. So therefore what you're going to get here, n times summation over Cn n. Remember, the summation of n only applies to these terms, not to this n here, times summation over m Cm star m. This summation only applies to this times m. So this comes out from here. And you will be able to understand, therefore, for only where n is equal to n, you will be able to pick up. For any other values, it will go to 0 because of orthonormality. So therefore, this ends up being Cn. Similar arguments here, only for m equal to m, you're going to get it. You're going to get Cm star. So therefore, this entire part, Cm star Cn, can be written as bra n p times m ket m, where p is the projection operator as defined here. So therefore, your expectation value will be given by a double summation m and n bra n p ket m times bra m a ket n. So if you pay close attention, this summation n goes over only these states, while this summation goes over only these states. So if we carefully look at it and rearrange this, for instance, let us write it this way: summation n p summation m ket m bra m times a times n. You are able to understand, we had seen earlier that this will be equal to E. So therefore, this entire term gets reduced to n times bra n p times a times ket n. I hope you are able to see both projection operator p and the operator a, which you want to observe, can be written as matrices. We just saw how operators can be written as matrices for Iz, Ix and Iy a moment earlier. And similar is the case for P. So therefore these two are matrices, and all you're trying to pick up here is the matrix element n and n for summation over n. This just indicates that this is nothing but the trace of the PA matrix. So that makes our life easy in the fact that if you want to make a measurement A, all that you got to do is to take the operator for A in the matrix form and the projection operator, take the product between these two matrices and find their trace, which is nothing but sum of their diagonal elements. We will see more examples of this as we go forward. Similar to all operators that you have seen in quantum mechanics, the projection operator P is also Hermitian in nature. That goes without saying. This will be useful as we go forward. Until now, we had the luxury of looking at an isolated spin half system, not worrying too much about the other degrees of freedom that exist in terms of the rotational, vibrational, and translational degrees of freedom. So called, we dealt with something called a pure state, where we only bothered about the nuclear spin. But in reality, all the others also contribute towards the wave function, and therefore we end up with something called a mixed state. Now, determining the wave function for this mixed state isn't straightforward or something that we actually need for NMR. So what we end up doing is to divide the system that we are talking about into nuclear spin system and the lattice. For historical reasons, the surroundings is what we call as lattice. As a result of this division, the spin wave functions for different molecules in NMR sample are no longer identical, but rather depend upon the hidden lattice variables. So we don't worry about any of the other things that end up coming here because all end up being part of the lattice. Each of this sub-ensemble that we have now generated will have their own time coefficients. If you remember, we were trying to see what is Cm star times Cn, the product, which will give us the projection, which when taken as a product with the operator that you want to understand will help you determine the measurable for a given operator A. But now with each of this sub-ensemble, we'll associate a probability density. So what we mean is that we are going towards more statistical terms right now, where we'll integrate over this entire probability of finding the system in that given state. So previously your definition of expectation value without the overbar had only this component, but the moment you go for ensemble averaging, the probability density ends up being represented here. So therefore, when you rewrite this, you're going to end up getting something of this sort. Summation over m, summation over n, integral p of psi times Cm star Cn times MAN with a d tau. So when you have something of this sort, you are able to understand the only difference between the previous time and this time is the ensemble averaging that you get, and therefore this will be rewritten as summation over MN with a Cm star Cn over bar times MAN, where this over bar indicates the ensemble averaging that we are trying to incorporate into this. Similar to the operator P that we had defined as the projection operator, and which is also given by Cm star Cn, NPM is given by Cm star Cn. Here we will be introducing the density operator, which will be denoted as sigma Nm. So this is nothing but Pnm. The ensemble averaging part will be now represented as this matrix called the density matrix times AMN. So what has finally happened here is that when you do an ensemble average, instead of taking the product between the projection operator and that of the observable operator, you are just trying to take the product of the density matrix with that to the measurement that you want to do. So this is an important aspect that we will be exploiting as we go forward. And sigma here is called the density matrix.